Well, I'm going to talk more about the functionality, customer-facing functionality than the operators. But of course, like everyone, a lot of this functionality is being developed as operators. So these things will be available in your modeler toolkit. But I want to show some of the stuff we've got here, you know, sort of in the new release. Now, in radar utilities, there's 4 new functionalities here I'm going to talk about. They exist both here and elsewhere in the software. A lot of things that we use in some of the automatic workstation functionality, we also put over here as freestanding utilities in case someone just wants to use them. Polarimetric classification I want to talk about first. We get pinged every now and then about polarimetry, you know, classifying multipolar radar data. It's something that is still a little bit more in the research world. I don't see a lot of applications for it, but it does come up every now and then. So I've been slowly building and fleshing out this package. So this is the utility now. We had it previously. It had only one, this thing called the polar ratio. So for 2016, I've added this thing I call a polar RGB, and most importantly, what's called a polybasis transform. Polybasis is one of those buzzwords that people know. They want to know, do we have a polybasis classifier? So yes, now we have it. To take a quick look at a multipolar data set. This is RadarSat-2. We look on the product XML. Okay, you can see I've got 8 bands here. So that's telling me that I've got all 4 polarizations. That's the most you can have, 4 quad pole. So I've got 4 polarizations, and I've got 2 bands per polar projection. So that means I have single look complex. So I've got a magnitude and a phase, SLC, for all 4 bands. So when I select this, I of course want to look at the mag layer. You can't really look at the phase layer and, you know, see much useful. So I want to look at my magnitude layers. Those are of course the odd numbers. So I'll make a 135 here. Okay, so that is looking at 3 magnitude layers of a multipolar data set at San Francisco. Here's, you know, Golden Gate Bridge, Oakland Bridge. Here's where everybody hangs out, the airport, etc. Okay, so when I call up this polarimetric classification tool, first of all, it's going to automatically populate with the scene I was just playing with. But the thing you have to do, well, you have to select which transform you want to use. But the important thing is you have to do the band assignments. And I can't know these a priori because different satellites do different things. But if you go to, oh no, get this thing out of the way, multispectral, this drop-down list will tell me what I have, okay? So HH, horizontal, magnitude is band 1, so HH is 1. VV magnitude is 3, so VV is 3, you know, et cetera, et cetera. So I can get these band combinations. HV is 5. So I can get my band assignments, give it an output name, hit calculate. This is what I call this generation 3 software where we use these GUIs, as opposed to generation 4, which is this real-time workstation stuff. Okay, polar ratio. So this is now the same scene. It's been classified based on what we call these bounce mechanisms. When the radar beam bounces, sometimes it rotates. So you transmit an HH, but when it bounces, it gets a little HV character to it. That's what we're playing with here, is looking at these, how things are bouncing, how they're interacting with the target. So this is the San Francisco area. It's been classified based on how the radar beam interacts with the stuff on the ground. And we can see, of course, the residential areas here. You know, you got a red component, that's a double bounce. We got the Golden Gate Park, and et cetera, et cetera. So this then is a, you know, classified radar image. And of course, there's a couple other, you know, classification algorithms in that package. Okay, continuing to play with the utilities. The next one is Sentinel Bursts. When I click this one, I'm going to input a Sentinel swath file, and it's going to break it down into the 6 or 8 or 10 bursts that comprise it. And I'm going to talk more about Sentinel a little bit later on, so I won't go into it a whole lot right now. I use this burst generator when I do all the processing, because we have to process Sentinel data at the burst level. Well, I'll talk about that in a second. I'm going to it right now. So this is just a freestanding burst generator, but we use it in our functionality. Okay. AutoEnhance. You guys should remember the AutoEnhance. It's been part of, sorry, give me a second here. AutoEnhance is one of those functionalities that we've had in this radar workstation for a while. You go to the radar analyst, you have a grayscale image, you hit this AutoEnhance, and it creates this, you know, quasi real-time enhancement. I've played with this before. I've shown you this stuff. You know, you zoom in, it recalculates. People like this algorithm a lot, but the problem was in this incarnation, you don't have any control over the processing parameters that I'm using. Because if you recall, what I'm doing here is I'm taking this grayscale image, doing 3 different enhancement transforms to it, and making an RGB. So in the new freestanding AutoEnhance, you have control over those parameters. So this, for example, the window size, that's the speckle filter reduction. The edge kernel, you know, how big of an edge kernel do you want to use? And the other enhancement is a nonlinear stretch. Well, what exponent do you want to use for your nonlinear stretch? So you can change these parameters around and optimize it. This is, again, a Generation 3 functionality. You'd input the image, give it an output name, set your parameters, and then calculate it for the full image as a final output product. The last one I want to talk about is the log ratio change detector. I'm going to talk a little bit about change detection at the end when I talk about the new SAR feature add-on module, which is going to do a lot of change detection, target detection, all that kind of stuff. But as part of that workflow, we developed this thing we call a log ratio change detector. Again, you just call up the GUI, input your 2 radar images, give it an output name, you know, and do the processing. Now, notice I let you select which magnitude layer you want to use, because like I just showed you, radar data can have up to 4 different magnitude layers: HH, HV, VV, VH. So we're starting to add magnitude layer control to a lot of these GUIs as we move into the era of dual pole or quad pole data. Anyhow, I'm not going to bore you with watching the calculation. So I'll take a look at the final product here. Give me 1 second to track it down. There's my log ratio image. So having input 2 radar images, I now have a change detection layer based on this log ratio algorithm. Pretty straightforward. I have my change bright. That's the kind of stuff I'm looking for. One reason I wanted this operator is because two reasons. First of all, I do get requests maybe once every month or so. Do we have a magnitude change detection for radar? A nice freestanding magnitude change detection. And the answer is yes. This now is your freestanding radar magnitude change detection. Phase change detection, you remember, is what we call CCD, coherence change detection. This is magnitude layer change detection. We had this previously, but we didn't really have what I considered a acceptable algorithm. I'm going to show you very quickly what we used to have, because this particular product is part of the product we call ILU. It's one of these CCD products, interferometric land use. You may recall it. Again, it's a 3-band, you know, color composite. And in this particular color composite, band 3 is the magnitude difference. Band 1 is the phase change difference. So this then is what we previously had for our magnitude change detection calculation. And you can see it's somewhat similar-ish, but one problem you'll notice is that sometimes change is dark and sometimes change is bright. And so I wanted to move into this new operator. I can swipe these two together. All right, so there's my old operator for magnitude change detection. There's my new operator. Okay, a crisper product. And so this is, as I just showed you, now a freestanding operator here. It's also part of this, what we call the ILU image, interferometric land use. This new layer has now been substituted into that CCD output product. And also, it's part of this new SAR feature change detection add-on module I'm going to talk about in a minute. So that's the new functionality that you have over here in under the utilities. The next thing I want to talk about is some of the interferometry changes that we've made. We have a couple things in here. I've done some upgrading onto the time series CCD, which we had in the past, and we have a new one called a Mosaic series CCD. Okay, so time series CCD we had in the past. A time series CCD is where we're watching a particular area, and we're getting imagery over and over and over again, and we start building up a time series stack. Let me load a project file I already have. There's a time series CCD of Gaza area, the Egypt, Israel border area. Everybody's kind of watching that. And you'll recall in this time series stuff, I can keep adding images. It automatically puts them into a date sequence and then puts them into pairs and makes the CCD products 1 to 2, 2 to 3, 3 to 4, 4 to 5. But we've changed this a little bit. We used to co-register 2 to 1, then 3 to 2, 4 to 3. We don't do that anymore. We now co-register all the images to the master image, number 1. And then we make all these CCD products. You recall, hopefully, that it runs through, and when it does the calculation, it turns green. Red means it didn't do this analysis. And then we had this display function where you could look at all these things you just created and display them in the viewer. That we've had since, 2014, something like that. We added a new tab for 2016, which we're calling post-process, okay? So I've created all these images that are co-registered to layer 1. And of course, I've created all these CCD products that are inherently co-registered. So I can now take and do what I call stack statistics. So I can say based on the input magnitude, the original input layer, or based on the coherence image, the CCD product, I want to create a couple products here. One of them I call M3, the min, the max, and the mean. Or median is what I always use instead of mean, personally. Or I can make an age stack, the oldest layer, the middle age, and the latest. Now, in this particular circumstance, I only had 4 images, so I really only have 3 products. So it's, nominally meaningless, if you will. But if I had, for example, 10, 15 images here, I've been watching this area over a period of time, these stack statistics start being kind of interesting layers. And I'm not going to create them right now. I'm just going to take a quick look at one of them, just to show you the kind of thing I'm doing, which Ian has already kind of oohed and ahed about. The age. So I've taken my magnitude layers, and I've put them in order based on the date timestamp. Okay, so we have here Egypt, Palestine over here, Israel here. Now, one reason I particularly wanted to show you this one, a couple reasons. One is, of course, beautiful colors, which everybody likes. And that's important, because if you're trying to pass information up to your higher, management levels, or people that aren't necessarily, imagery savvy, particularly radar savvy, colors, are interpretable to them. Radar bounces or not. So that's one reason I wanted to put it here, because of the color. But the other thing is it brings up a point that, once again, I get pinged on every now and then. People want to do vegetation mapping. They're always asking me, how do I do vegetation mapping? And the answer I always give them is, you have to understand the growth cycle of the plant and use that. And so that's why this age image makes a nice example here, because age is kind of a function of the growth cycle of the plants. And as you can see, we get very different responses based on the different growth patterns, if you will, of the crops within these fields. So this kind of demonstrates several points simultaneously. But this then is based on stacking together the magnitudes after we've co-registered everything. So everything is co-registered here at 100th of a pixel. So we have very fine co-registration, and then we've layer stacked them based on the age, the time, and you can see the kind of product we get here. So that's the new stuff we added to time series, CCD. The other one I want to talk about is this thing we call a mosaic series CCD. Similar in concept, except for instead of having a time series, we have a mosaic series. Again, sometimes people are monitoring a large area. Maybe it takes 2 or 3 or 4 images to monitor their entire area. They want to mosaic these things together. So that's what this tool is for. But one of the main driving factors for putting this tool together for 2016 is Sentinel data. If you guys are familiar with Sentinel, it's a new radar satellite launched by the European Space Agency. There's actually 2 of them up there now, Sentinel 1A and 1B. The interesting thing about this sensor, of course, is that the data is free. That attracts a lot of attention. The disadvantage is it's 30-meter pixels, which limits its use in a lot of cases. Just to look at this very quickly for 1 second, I'm going to show you a PowerPoint, but not very much of it. I will, if you want, I'll give you this PowerPoint. I'm probably going to update it a little bit. This is the imaging mode for Sentinel. It's what's called interferometric wide swath. If you look at the image name, you'll see IW, interferometric wide. That's the standard imaging mode for Sentinel. And this, if you look at the imaging mode here, this beam is jumping all over the planet in order to capture these images. This causes a very complex data set. So this is a full scene. A scene is comprised of 3 swaths, as you see here, and each swath can have 6 to 10 bursts. So a full Sentinel scene can actually be comprised of 30 bursts. Each burst is like what you might call like an imagette, if you will. Now we have to import and process these things at the burst level. That's why you saw me use this word burst. And I showed you that tool we had that would break a swath into the bursts. So we have to process, when we say we're going to do CCD, we have to process at the burst level and then mosaic all these things together. So that's why we had to put together this tool. And like I say, I have a whole PowerPoint here. I'll update it a little bit, and people who want it can let me know. Here, for example, I'm showing using an entire swath. So I've read 6 or 8 bursts in. I'm using my histogram tool here to do flood mapping. So all this Sentinel stuff works in the workstation. Here I've taken a full swath. I've displayed the swath. It's co-registered on the fly. I've got my 6 or 8 bursts here, and I've used that AutoEnhance algorithm I was just talking about. So we can handle all this Sentinel data in the Radar Analyst workstation. I don't have time to go into it a whole lot right now, but here, for example, I've loaded in all 10 bursts. But when I use my AutoEnhance, of course, it treats each one as a separate image. A lot of complexity in using this stuff. I don't have time right now. I will update this PowerPoint and give it to you later on. But going back to Imagine, which is where I wanted to focus, we have here this mosaic series, CCD. So you could, for example, you could mosaic RadarSat data, TerraSAR data, Cosmo data, whatever you had to work on. But for right now, I want to talk a little bit about Sentinel. It was our focal point for this tool because we had to have it. So if I say I want to do Sentinel, it pulls up a little sub-tool, and I would have to input my reference and match swath. So I can input a swath, 6, 8, 10 bursts, whatever it is. Now I would give it a project file name. So I'm going to load a project file that I've already done to save your time. And since I only have 10 minutes. Okay, here's the data set I'm working on right now. because it's an area of interest. I'm putting together a tour guide that I'll make available for people in the defense world. This is Palmyra in Syria. What this software has to do behind the scenes, when I throw in a reference image and a match image, it goes through and calculates the footprint on the ground, the geographic footprint of every burst in both swaths. And then it pairs them up as best it can. So in this particular instance, you can see my reference is burst 0. You know, they can't start with 1, they got to start with 0, right? These are scientists. But it's with match burst 1, okay? And then for the next one is going to be reference 1 with match 2, et cetera, et cetera. So it's going to run through that whole cycle and put these footprints together. After it does that, it takes the reference and match that is paired up between these two swaths, and it creates CCD project files. Using your edit template, you can put together whatever processing parameters you want to use. Defaults are usually pretty good, but here you'll select the products you may particularly want to make. Right? You can filter or not filter them. We can do our standard coherence. We've got the interferometric land use, multi-temporal coherence, coherence texture. These are those color products that we're making out of the coherence image that are, you know, easier to interpret, put the information into your face easier. Okay, you're familiar with this? I've done all these workflows, so these have all been processed all the way through coherence. We get to display, and now I can display anything that I've created. So in this case, I can say, okay, I want to display the coherence layers. Well, let's do the ILUs of all these different bursts. So you can see down here, it's loading the ILU product from all these separate bursts that it's processed. Okay. You can start to see why these products like ILU, coherence texture, are much more interesting than looking at grayscale coherence layers. Okay, here we have a lot of color-coded information. So these are all loaded as separate swaths. And you can see, for example, we have, you can see the lines between these swaths because, of course, each little swath is a separate imagette, and it's got its own lookup table. So we've added, again, this post-process step where I can mosaic these things together, make a seamless mosaic. And again, I can select which product I want to mosaic and whether or not I want to do a filtered or unfiltered version of it. Again, I have this thing already made if I can find it. Okay, so now it's mosaicked and I've gotten rid of the lines. Now, one thing I want to point out here, because a lot of people have been contacting me about this data, that's why I'm putting together this demo. What can you really see? It's a beautiful image. It is showing you stuff on a regional basis. Sentinel is kind of a regional synopsis. What we're looking at right here is the city of Palmyra, where all this damage has been going on, and we know all about that. As we start zooming in, of course, with 30-meter pixels, the world gets pixelated. So, can we detect ISIS chopping off people's heads? Not really. So there's uses for Sentinel. How far it's going to push into the surveillance and defense world, I'm not really sure right now. We're still kind of playing with that, but that is some of the functionality that we put in there for to support Sentinel. So, in general, Sentinel is well supported. We read it. We read the single complex. We read the geocoded. It's geocoded. The SLC is geocoded directly into the viewer. The radar analyst workstation can process it. You can ortho-correct it. And we have these, and CCD has a real strong product generation capability with it. So, we're supporting Sentinel real well. One more thing I'm going to touch on here, just very, very little, because I don't have a lot of time, and it's not really something we're supposed to talk about today, because this is 2016. We have this new module I've alluded to a couple times, this SAR feature extraction. It's going to be in 16.1. Just to give you a very quick look at it. In this is a real-time workstation, and we're talking about very real-time. If I have a fast computer with GPU, CPU processing, I can despeckle an entire TerraSAR-X image in maybe 1 or 2 seconds. Okay, so we're talking about seriously fast processing. Real-time change detection, real-time target detection. Load these things as a raster chain. Sorry, give me 1 second here. Okay, so I now have this whole new tab called SAR Feature. My image is read, geocoded into the viewer. This is a Cosmos SkyMed, but not only is it geocoded, it's already despeckled, because despeckling is done automatically in this workstation. It's part of the functionality. This is a workflow workstation, so I can do several steps. I won't have time to go into it right now, and I don't have a fast CPU, GPU computer anyhow. But as I say, it's already despeckled. I zoom in, it's automatically despeckled. This is not a simple despeckle algorithm. This despeckle algorithm goes all the way through despeckle into the world of anneal. And I can control that mostly through my smoothing parameter here. I can emphasize point targets. People in the defense world like point targets. People in the classification world want to kind of suppress those. I can do that. But I can change this smoothing parameter. And with a fast computer, this would already be despeckled at the next level. And I'm pretty slow here, so I don't want to, but I don't know if you saw that. This is set up to automatically set everything to, I can automatically go to a 1-to-1. That's because I'm doing, pixel level processing, and I want to observe things at that level. But let's see if I can go a little higher here. Yeah, did you see it smooth it? Other people seeing that? So you can imagine, time we get up into these hundreds, you've got to seriously, as I say, way beyond despeckling into annealing the image. Well, why do we want to do that? Because this is only the pre-processing step. After you do this despeckle, you can then move into things like target detection, change detection, or feature extraction. Look how far we've gone into the world of despeckle. This is no longer despeckling. This is annealing. Very sophisticated algorithm. I won't go into it a whole lot further here because it does take time to do this processing. See if I can just do a quick change detection here. So I have now added target detection on top of despeckle. So my image is being despeckled. So first of all, I optimized my despeckling, and then I pushed it into a target detection. Right? Again, if I don't like it, I can change these parameters, and it's going to despeckle it and do target detection. As you may have seen, there's 2 different target detection algorithms here with some various parameters to it. The other thing I can do, I won't go into it right now, I can put 2 images here, and then I have change detection. There you see that log ratio again. I also have the blue is new, which you know, and we have a very sophisticated one called a sparsity algorithm. And the final thing I can do is I can actually move into shift extraction here. And I don't have time to go into SAR feature right now. It's going to be 16.1, but as you can see, there's been a lot of work on radar. The operators are there, but the work has really been done on the user interface and getting this functionality into a real-time or quasi-real-time world where people can do stuff in a workstation environment. The radar analyst workstation or the new SAR feature workstation. Extract the information, make a shapefile, make a color image, and get it off to your management to make a decision and move forward. Operational information. Okay, that's all I have time